We will begin our study of several important types of discrete random variables and their probability models. The dichotomous experiments result in two possible alternatives for responses. So that means we may be able to answer questions such as yes, no, or pass, fail, defective, non-defective, or male, female. There are just two options available in all those examples, so those are dichotomous experiments. Our first type of variable that we'll talk about in this section is the binomial random variable. And that means we will talk about the number of successes in n number of trials. So to break that down, it means we're going to have a fixed number of n times that we will conduct the experiment. From those n number of times, we're going to observe the number of successes. In other words, we're going to observe the number of x times that one of the two possible outcomes occurs. And this is the binomial experiment. There are exactly two outcomes for each trial of interest. Either the event will happen or it will not happen. Now we do have a formula here that will help us to actually calculate a probability. So the formula tells us about the probability of x occurring, and that is equal to n number of trials, x successes that we are testing for. So the x here is the same as the probability of x that we are trying to determine. And that is multiplied by p raised to the power of x. So p represents the probability of success raised to the power of how many successes are we looking for, multiplied by q, which is our complement. So q is raised to the power of n minus x. N minus x represents what is left over once you've already considered the number of successes. So we are taking the total number of trials minus the number of successes. So what we're left with is not success. Each of those variables is broken down here. Again, as I said, p is the probability of success for the single trial. Q is our complement, and that is calculated by taking 1 minus p. N is our total number of trials, and x is the number of successes in those n trials. So you notice that this portion, n over x, that is our factorial. Now we can use factorial on the calculator, or we can just write it out, and I'm just going to work this out longhand for you to see exactly where this value is coming from. Now let's look at an example of how this is used. For the first problem, we have x is a binomial random variable. Again, binomial random variable means that there are going to be two outcomes possible. Either the event happens or it does not happen. We're going to compute the probability of x for each of the following cases. So in example A, we have n is equal to 5. That means there's a total of 5 trials. X equals 2. That means we are looking for the probability of 2 successes out of n number of trials. So 2 successes out of 5 trials. P is our probability of success. So we have given p-value of 0.4. So what we need to calculate is the value of the complement, or Q. So Q is found by taking 1 minus the p-value. 1 minus 0.4 would leave us Q is equal to 0.6. So we're going to substitute these values into the binomial probability formula. So the probability of 2 successes is equal to 5 trials. We're looking for 2 successes, and that is multiplied by 0.4 raised to the power of 2 times 0.6 raised to the 5 minus 2. So 5 minus 2 will ultimately give us an exponent of 3. So let's break this down. 2 successes out of 5 trials means we have 5 factorial divided by 2 factorial multiplied by 5 minus 2 factorial. So all of these values here are coming from expanding the factorial. 5 factorial is 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1. And 5 minus 2 factorial is 3 times 2 times 1. So you can see here in red, we have some common factors to reduce. So 3, the factor of 2, the factor of 1, all clearly reduce. But we also can reduce 4 with 2. So 4 is the same as 2 times 2. So one of those 2's reduces with the 2 in the denominator. So what we have not reduced yet is 5 times 2 times the rest of our binomial. So 5 times 2 will give us 10. And then 0.4 squared gives us 0.16, and 0.6 cubed gives us 0.216. So if we multiply these 3 factors, the probability of 2 successes equals 0.3456, which is kind of an interesting set of consecutive numbers there for the answer. Let's try another. In B, n equals 6 means there are 6 trials. X equal to 3 means we're looking for 3 successes out of the 6 trials. P-value of 0.8 means our probability of success is worth 0.8. So to calculate Q, that would be 1 minus the p-value of 0.8. So Q is worth 0.2. So you can see that 0.2 is going to be substituted. P-value is substituted. And n is our number of trials, so that's our 6, and x value of 3. So the way we would interpret this is the probability of 3 successes is equal to 3 successes out of a total of 6 trials multiplied by the probability of success, 0.8, raised to 3 successes multiplied by our complement, 0.2, raised to the complement. That is 6 trials minus the 3 successes gives us leftovers. Those leftovers are the complement. So 6 minus 3 would become an exponent of 3. So to break this down, 3 successes out of 6 trials, we're using factorial. 6 factorial, 6 times 5 times 4 times 3 times 2 times 1, divided by 3 factorial, that's our 3 times 2 times 1, multiplied by 6 minus 3 factorial. So that would become 3 times 2 times 1 again. So you can see in red we have identical factors. We reduce those factors. Now look to see if anything else can reduce. Notice I've already written in green that 3 times 2 makes 6. So 3 times 2 can reduce with 6 in the numerator. That leaves us 5 times 4 not reducing with any other factors. So 5 times 4 will give us 20. And you can see I've written 20 right here below. Then we have our 0.8 cubed makes 0.512, and 0.2 cubed is 0.008. So when we multiply these 3 factors, we get the probability of 3 successes is equal to 0.08192. And typically we cut this off at 4 decimal places. So we would have 0.0819 for the final answer.